So welcome to video 9.1.1, the first in our 9.1 lesson, all about molecular shapes and polarity. So the first thing we need to understand is what electronegativity is and how to use it. So electronegativity is a value assigned to an element anywhere from 0 to 4, combining its ionization energy and its electron affinity. And that describes how much an atom or of any element will pull on an electron from another element during a covalent bond. Now, these can be really helpful in determining the type of bonding that takes place between atoms. And if you look on the very last page of these notes, you will see that you have a table of electronegativity values. It is definitely worthwhile to memorize the first few in this general vicinity over here, as well as hydrogen. And then also to, of course, know the trends. Now, if you have any two of these elements together and they have a bond, you can look at the difference of their electronegativities and kind of figure out the type of bond that happens between them. So if you have a difference of 0 to 0.4, so for example, hydrogen bonded to carbon, the difference is 0.4. That's going to be a nonpolar covalent bond. If you have a difference of 0.5 to 1.7, anywhere in that range, you'll likely have a polar covalent bond. The bigger the difference, the more polar it's going to be. So if you look, for example, at hydrogen and oxygen there, you have quite a large difference. And so because you have a bigger difference, it's going to be a polar covalent bond. So if you have something that's 0.45 or so, it's really kind of in the middle. So this isn't just some set cutoff. This exists on an entire continuum, right? So we're going from not very polar at all to super polar. And then, of course, anything that's got a greater difference than 1.7 in general is pretty much an ionic bond. Okay, so reviewing that and having that handy will be helpful for you for the rest of these notes. So in our first example, we're going to consider these four compounds here and their melting points. So these are the point at which they melt. And then we're going to fill in the chart based on what we see in the melting points. Now we're going to need to use our knowledge of intermolecular forces to figure out how to deduce the bond type, the Lewis structures, everything from all these melting points. So first let's start with hydrogen, H2. And I actually want to go and switch to the Lewis structure first. So H, that's our Lewis structure, right? And so if we look at this, hydrogen and hydrogen, bond, hydrogen and hydrogen, we're going to have a difference of 0 there, because 2.1 minus 3.1 is 0. So this is going to be a nonpolar covalent bond. So nonpolar covalent bond. And when we have something that's nonpolar, within that bond, we're going to say that those electrons are shared equally. So electrons, negatives, are shared equally. Okay, so use the bond type and the Lewis structure to explain the melting point. Well, the only kind of intermolecular force you're going to have here are those London dispersion forces, London dispersion forces. And so those London dispersion forces are pretty weak. They're the weakest of the intermolecular forces. So that means they're going to have a really low melting point. So it's very, very easy for this to melt, which is why at room temperature we see hydrogen as a gas because it's already much hotter than its melting point. So weak London dispersion forces. That means we're going to have a really low melting point. And these molecules are just governed by their intermolecular forces. Okay, now let's look at HCl, hydrochloric acid. It has a melting point that is slightly higher. So let's go over to its Lewis structure and see what we have here. So we have hydrogen bonded to chlorine, and look, we have all of those electrons surrounding chlorine. So if we go and we look at our electronegativity values table, we can see that chlorine has got a value of 3.0, hydrogen is 2.1. So the difference there is 0.9. So we know we're going to have a polar covalent bond. Another way we can deduce that is just by looking at where these electrons are localized. So we can see that chlorine has a ton of electrons all around it over here. So we can see that there's definitely some polarity happening in this molecule. So this is a polar bond that is polar covalent because those electrons are being shared. We have a difference of less than 1.7. And so these electrons are shared unequally. Shared unequally. That means we're going to have some polarity happening here. So what attractions do we have here? So now we have, since this is polar covalent, we're going to have dipole attractions. Those are kind of medium. They're kind of intermediate in the intermolecular force kind of continuum of strength. So these have a lowish melting point. I know, very scientific, lowish. The molecules here are governed by intermolecular forces again. Okay, so sodium and potassium here, well, these are both metals, so we're going to know right away that these are metallic bonds. And we know that in metallic bonds, the electrons are shared in that sea of electrons. They are delocalized. So we have delocalized electrons here. And so because of that, we don't really have a Lewis structure. We could draw a crystal structure with sodium and potassium everywhere and electrons delocalized, but there is no formal Lewis structure for metallic bonds. And so these are reasonably strong, because these are no longer intermolecular forces. These are metallic bonds. So because of that, they have a medium melting point. And so just to give us, just to remind us up here, this is an intermolecular force. This is an intermolecular force. And this is a natural bond. Okay. Now going down finally to sodium chloride, we can see we have an insanely high melting point here. So it's really, really hard to melt salt. So what's happening here? Well, if we look at sodium and chloride, even just going back to our table, chlorine is 3, sodium is 0.9, so we have a huge difference of 2.1 there. That's going to be an ionic bond. We can also tell this is ionic because we have a metal bonded to a non-metal. So this is a ionic bond. And chlorine is now chloride in this bond, and sodium is now the sodium positive ion, an A+. And so when you have your sodium and your chlorine all together, you can draw that we have our sodium ions attracted to our chlorines. And don't forget your valence electrons here, because now this is chloride, so it's got an extra electron and it's negatively charged. So you can draw these in a huge crystal structure here, and they are insanely strong. They have very strong electrostatic attractions. They have the highest melting point because you have that really strong repeating positive, negative, positive, negative, positive, negative, and that's just repeating end on end on end in this entire crystal. So that is a lot of attractive forces happening there, very close together. So these are very strong, the strongest. They're very strong, electrostatic bonds. It's an ionic bond. And this is the highest melting point. And that word electrostatic just means positive attracting negative. That's all. Don't get tripped up on that. Okay, now let's take a look at the Lewis dot structures. For this part, since you have already practiced with Lewis dot structures, I would like you to please pause the video and see if you can fill in all the Lewis dot structures. Now I will tell you or give you a little hint. For these last two, there are 2 structures each that are possible because we have resonance happening here. So I want you to draw both structures in here and both in here. The rest just have one. Okay, so for now, please go ahead and pause the video and try drawing your Lewis structures. All right, welcome back. Let's go ahead and check our work. So here we have our carbon kind of in the middle. We have our hydrogens all around it. And we can tell kind of the way to draw this, really with any hydrocarbon, they tend to go in order and kind of like give you a hint at what the Lewis structure will look like. So we have the CH3 first, CH3 right here, bonded to that hydroxide functional group. So CH3OH. And then, of course, don't forget the alone pairs on our oxygen. We want the greatest separation possible there. Okay, for CO2, carbon's going to go in the middle. You're ending up with double bonds here. Now let's go ahead and draw these electrons as far away from each other as they can possibly get. Okay, boron trichloride. So the boron, there's only one of them. I'm going to go ahead and put that in the middle. Draw my chlorines all around the side. And their lone pairs surrounding it. Now remember, boron is one of those exceptions to the octet rule. It tends to like to have 6 electrons around it. So right here, that's why we have our 3 bonds that are covalent, so a total of 6 electrons. Okay, sulfur oh gosh, the name is escaping me right now. Give me a moment. Okay, so our sulfur, we have one of them, the right in the middle. Tetrachloride, sulfur tetrachloride. Sorry about that. Couldn't think about tetra for a second. Okay, so we have all of our extra electrons around here as well. Now, sulfur is one of those elements that has an expanded octet. So this is another exception to the octet rule, right? We have a ton of exceptions. And so our extra 2 electrons should go around sulfur. They need to be paired. Make sure you're not drawing them separated because they are paired. Okay, now let's get to our fun ones. Anytime you have an ion, don't forget that you need to draw brackets. So anytime you have a charge up here, your ion belongs in brackets. So our first one, oxygen, nitrogen, now and a double bonded oxygen over here, and a negative charge. Don't forget to draw your remaining lone pairs here and here. Now we can see that we can also possibly have the mirror image of this. So let's go ahead and draw the other option. Don't forget the brackets happening there. This is a resonance structure. So this can be either one of those 2 structures, and we will learn in the next lesson what this truly looks like. But for now, we can say that there's 2 possibilities here. Same thing happening for NO2 over here. So we have our nitrogen. Now this one's an interesting structure, as we're going to have a lone electron. So don't be afraid of that lone electron. Once in a while that does happen. That is a free radical. We've heard of free radicals before, probably in our daily lives. So a free radical is just a lone electron, quite reactive, doesn't like to stay in this state for long. Now we'll notice that we have this mirror image possible once again. So we can draw the other option with our nitrogen in the middle, of course, because there's only one of them. So those tend to go right in the center. And then, of course, we still also have our lone electron. I'm going to stick it right there because of my arrow. Okay, so those are our Lewis dot structures. Now, the question comes up. If you can draw multiple Lewis dot structures, which one is the most likely? Which one is the best structure? That is where formal charges come in. Now, formal charges are going to help you so much. Formal charges, we can calculate. We can just do some simple calculations. And from those little easy calculations, we can figure out which structure is the most likely for any of these. So let's see what we do. So the formal charges are the charge on each atom that each atom would have if all shared electrons were actually shared absolutely equally among the molecule. Now, to calculate that, you'll take the number of valence electrons minus the non-bonding valence electrons, meaning your lone pairs, essentially, anything that's not involved in a bond, and 1/2 of the bonding electrons, so each bond. And the sum of all the formal charges is the total charge on the compound. So if we have this compound that's -2, the sum of all of our formal charges should add up to -2. If we did the formal charges for NO2 minus over here, all of your formal charges should add up to -1. The more negative formal charges should be on the more electronegative atom. And so we have our table of electronegativity values here. You also have memorized the trends. So we want the more negative numbers on the more electronegative elements like fluorine and not so much on things like cesium. And the more stable structure minimizes the formal charges on atoms. So you want the atoms to have the smallest number of formal charges possible. So let's go ahead and take a look at an example. So let's do CO2. So we'll have our carbon here, our oxygen there, and our oxygen there. And now I have a double bond between each CO2, so I'm just pulling from this structure over here. And a bond consists of 2 electrons. So I'm going to write that separately. I'm going to show them separately here just to kind of show us where everything's coming from. So 1, 2 bonds. Our lone pairs of electrons there. 1, 2 bonds there. And our lone pairs of electrons. Now I want to separate out these electrons. So I'm going to draw a line right here so I can show you where everything's coming from. Aha. So we're looking at each individual atom. Let's go ahead and zoom in so we can take a look at what's happening. Okay, so the first thing we're going to do is write down the usual number of valence electrons that each of these atoms would have. So oxygen has 6 valence electrons. We can look at that and pull that from the periodic table. So we've got 6 electrons there. Carbon normally has 4 valence electrons, and of course our oxygen, again, has 6 valence electrons. So how many electrons are there surrounding this atom in this particular structure? So let's go ahead and label this. So this is the, so we don't get confused here, usual number of valence electrons. And then below, we are going to subtract the number of valence electrons that are actually in this structure. So that's the reason I drew lines right here. So oxygen has 1, 2, 3, 4, 5, 6. So minus 6. Carbon has 1, 2, 3, 4. So we see that it's sharing, but we're not counting the shared electrons here. We're taking into account this 1/2 bonding electrons. That's where that comes in. So minus 4. Then our oxygen, again, has 1, 2, 3, 4, 5, 6 around it. So minus 6. If we do the math for all of these, we end up with 0, 0, and 0. And so we can see that if we have 0, 0, and 0, that is minimizing the charge down to 0 on each atom. So that's why CO2 is so stable in this configuration. Let's label this so we remember where these came from. So this is the number of valence electrons in this particular structure. Sorry, it's a little bit small. Okay, so now let's go ahead and do some practice problems. So this following structure for SO4 2- sulfate has 3 possibilities here. And the question is, which one is the most likely? So let's go ahead and pause the video right now, and I would like you to try to figure out the formal charge on all 3 of these, and then come back and let's check your work. All right, welcome back. So here we have a sulfur in the middle and 4 equivalent oxygens bonded to it. That means the oxygens are all single bonded and they all have 6 electrons. So I'm only going to be looking at our sulfur here, and I'm going to be looking at an oxygen. They're all equivalent to each other. Sulfur normally has 6 valence electrons. Oxygen also normally has 6. We pull that from the periodic table. Now, how many are there around sulfur in this particular structure? Remember, each bond has 2 electrons, like this. And if I just count half those bonding electrons, or just the ones that are just around the sulfur, immediately around it, I'm trying to draw this in between, we can see we have 1, 2, 3, 4 electrons there. So sulfur, 6 minus 4. Oxygen, how many do we have around oxygen in this structure? 1, 2, 3, 4, 5, 6, 7. So minus 7. Okay, and we notice that all our oxygens are equivalent here, so every oxygen is going to have exactly the same mass. So we're all done with that. 6 minus 4, that's 2. 6 minus 7 is negative 1. So let's do the next one. For this one, we also have our sulfur, but look, we have 2 different kinds of oxygens here. So we have double bonded oxygen and single bonded oxygen. So I'm going to differentiate between them. So double bonded oxygen, single bonded oxygen. So these are double and single bonds. That's what that means. Okay, so each of these have 6 valence electrons. Now let's count the number that is around that are around each atom. So let's look at our sulfur here. Actually, I don't want to change color. So sulfur has 1, 2, 3, 4, 5, 6. There are 6 bonds, and half the bonding electrons is 6. Remember, the other half are around the oxygens. So 6 minus 6. Now let's look at our double bonded oxygens. How many do we have there? Well, 1, 2, 3, 4, 5, 5, 6. So minus 6. Now let's look at our single bonded oxygens. 1, 2, 3, 4, 5, 6, 7. So minus 7. All right. So 6 minus 6, 0. 6 minus 6 is 0. 6 minus 7 is negative 1. Okay, now let's do our last one. Now we only have one kind of oxygen and one kind of sulfur. So we have a sulfur and we have a double bonded oxygen. We don't need to differentiate that because we only have one type of oxygen. They're all equivalently double bonded. So again, these each should have 6 valence electrons in their neutral state on the periodic table. Right now, let's count. We have 1, 2, 3, 4, 5, 6, 7, 8 around sulfur, so minus 8. Oxygen has 1, 2, 3, 4, 5, 6. Minus 6. Okay, so sulfur is negative 2. And oxygen is 0. So right now, even if you didn't get these numbers, I'd like you to pause and try to figure out which one of these structures is the most likely to be the real or the most stable structure, and why. And then come back and check your work. All right, if you said this one is the most likely, you are correct, because this has the smallest formal charge on each of the atoms. So this one, smallest formal charge therefore, most likely. Now, the absolute worst case that we could get is this one over here. Because if we look, this -2, the more negative number is around the least electronegative element. So if we look at the electronegativities of oxygen, 3.5, and sulfur, 2.5, so the more negative charge should be around oxygen. But in this case, it's around sulfur. That's very bad. And so this one is quite bad. And that's because the less electronegative atom has a negative formal charge. Okay, and that's how you figure out the most likely Lewis structure when you have many choices of possible Lewis structures. All right, that's it for video 9.1.1. See you next time for 9.2.2, or 9.1.2 rather.